Hello, everybody. My name is Jonás Chaves-Montero, and I am a postdoc at the High Energy Physics Institute in Barcelona. I'm going to talk about the lensing slope problem. But before I do so, I would like to introduce my collaborators, Raúl Angulo and Sergio Contreras. So what's the lensing slope problem? This is a discrepancy between galaxy-galaxy lensing measurements from observations and prediction from empirical models fitting galaxy clustering. So the idea is that you select a particular sample of galaxies, in particular both galaxies, you use your favorite empirical models to fit their clustering, and then you use this model to predict the galaxy-galaxy lensing. You compare this prediction with observations, and what you find is that there is a strong discrepancy of around 30% on a small scales. You can see this in the right panel here, that different lines correspond to different empirical models. The diamonds correspond to observations, and you can see there is a huge discrepancy in small scales. And we can also see this in the left panel, which shows the ratio between galaxy-galaxy lensing measurements and predictions from these empirical models. And again, the ratio goes from around 20 to 30%. And by the way, unity would mean that the model predicts exactly galaxy-galaxy lensing observation. So before we study this problem in more detail, let's do a recap of how empirical models work. So the first thing that you need to do is to select a target data. In this case, we are going to select the projected clustering of both galaxies, a simulation in which you evaluate the empirical model. This is very important because this simulation is going to set the cosmology of the problem, and the empirical model per se that you select. There are different flavors. The typical ones are HODs and SAM. These models, what they give you is the galaxy-halo connection. So in which way galaxies populate the halos from the simulation. The next step is to optimize the model to reproduce the target data. To do so, the first thing that you do is to select a particular value for all the parameters of the model, evaluate the model in the simulation, creating a mock galaxy sample. Then you measure the target summary statistic in the galaxy from this galaxy sample, and you compare it with observations, and in that way, you put a point in the posterior parameter space. So you repeat this process again and again within an MCMC framework and set constraints on the parameters of the model. Finally, for the best fitting parameters of the model, you populate the simulation again and predict galaxy clustering and galaxy-galaxy lensing. And this is your shield, you see. Why is it a big deal that when you fit galaxy clustering, you can't predict galaxy-galaxy lensing precisely? This is because both observables are sensitive to the same underlying galaxy-halo connection. So if you have a good model for the galaxy-halo connection and you are able to fit galaxy clustering, in principle, there are not other degrees of freedom modulo baryonic effects. I'm going to talk about that later in the problem. So if you fit galaxy clustering, you should be able to predict galaxy lensing as seen in observation. So the possible solutions for this problem. The first one is that it's cosmological. There is another phase of the SA tension. So this is the discrepancy between measurements of the amplitude of matter perturbations in the universe from early universe studies and from late universe studies like DES or other lensing surveys. As you can see in the figure, there is a sigma discrepancy. So what it could be happening here is that because we are evaluating always the model in a simulation with a Planck cosmology, it is possible that in reality the cosmology is different. So we should evaluate the model in a S8 in a simulation with a low value of S8, and in that way we will solve the problem. In fact, people have shown that this alleviates the problem, right? Doesn't solve it completely. And the other possibility is that it is astrophysical, is that the models that we are using for modeling the galaxy-halo connection are not sophisticated enough. And one example of why we think so is that standard HOD models don't include any galaxy assembly bias, but this is something that we measure in different aerodynamical simulation and semantic models. For example, here I'm showing the results for the Eagle aerodynamical simulation. And this assembly bias is the difference between these lines and zero. And you can see it's at around 20%. So this is in changing galaxy clustering by around 20% on scales of the order on a small scale. So this could be another option. In order to solve the question of which one is the best explanation, what we did is to study this problem under control conditions, exactly using the illustrious TNG simulation. Why the simulation? Because the volume is large enough for the statistical studies and because it reproduces a lot of important problems that we care about from observations. For example, broadband galaxy colors and the clustering and red and blue galaxies. We are especially interested in the clustering of massive red galaxies because most galaxies are like that. As you can see, the bottom panels, the simulation gives very good prediction for the predicted clustering of SDSS galaxies around 0.1. But the point is that red galaxies, the red points, for galaxies for very massive galaxies. So the next step was to draw a sample from this simulation that has similar characteristics at most galaxies from observations. And in order to do that, what we did is to apply the same color-based selection criteria as the ones were applied for selecting both galaxies. So this sample, this both TNG galaxy sample is going to be our target data, specifically the projected clustering of these galaxies. Our simulation, the one in which we are going to evaluate the empirical model, is a gravity-only version of the TNG simulation, so same cosmology in both simulations. And the empirical model is a standard implementation of an HOD model, very similar to the ones used in lensing slow studies. And what these HOD models do is to populate the halos from the simulation with central and satellite galaxies. So what did we find is that we were able to fit very accurately the clustering of this sample of galaxies using this very simple empirical model, but we were over-predicting the galaxy-galaxy lensing. So we were reproducing the lensing slope problem for the first time under control conditions. And given that we were using as target data galaxies from the TNG simulation that it uses a Planck cosmology, and we are evaluating the model in a simulation with a Planck cosmology, the only origin of the problem could be astrophysics, because we were fixing the cosmology. And the other important point is that, as you can see in this sample, that is again the prediction from the measurement from galaxy-galaxy lensing over predictions. The results that we get from the TNG simulation, that are the black dots, are very similar in amplitude and scale dependence and the measurements of this ratio from observations. So this is also telling us that the TNG simulation is doing a good job in reproducing the galaxy-halo connection of galaxies from observations. Yeah, once we were able to replicate this problem, we wanted to know the origin of the problem. In order to do so, we started to study all the different assumptions of HOD models. For example, we were checking whether the mass dependent of whether the galaxy occupation was only mass dependent, or there were further dependencies on other properties. So whether there was a galaxy assembly bias or not, whether the satellite galaxies were really tracing the distribution of matter within halos, as it usually assume, or in reality the distribution was different, the impact of baryonic effects on the Riemann scale that we care about. And what we found is that none of these assumptions of these standard HOD models are fulfilled by the post-TNG galaxies. So the distribution is different, they have a sensitive level of galaxy assembly bias. So we had to study whether all these assumptions that were broken could result in the lensing slope problem, or maybe not. Maybe there was a different origin for the problem. So to do so, what we did was to create different samples fulfilling different range of assumptions from each of the models. We evaluated the traditional model, always using the same 5-parameter traditional model, in a gravity-only version of the TNS simulation again, fitting galaxy clustering and predicting galaxy-galaxy lensing. And this is what we found, that as we were considering the breaking and more assumptions, galaxy formation assumptions of these models, we were increasing the discrepancy between galaxy-galaxy predictions and measurements, to the point that after considering all the different galaxy formation effects that we found important for galaxy clustering and galaxy-galaxy lensing, we're able to reproduce the same lensing slope problem as the one found from observations. So this is what we get after accounting for the different effects. It is shaded area. It is a shaded area because we consider different types of baryonic effects. As you can see, this shaded area agrees very well with the triangles that are the measurements from observations. So what is really happening here is that these empirical models are very flexible and they can fit galaxy clustering even though they are not modeling this effect. But to accommodate for the impact of these effects in the galaxy-halo connection, they overpredict the galaxy-galaxy lensing. So in reality, they are assuming a wrong galaxy-halo connection, and because of that, the prediction for galaxy-galaxy lensing are also wrong. Now that we know the origin, the next thing that we did was to try to solve the problem, not only in simulation, but also in observations. So because the origin of the problem is that the standard empirical models are good enough for fitting a galaxy clustering and galaxy-galaxy lensing jointly, what we did was a more sophisticated model. And we selected the subhalo abundant matching extended. That is a subhalo abundant matching model with additional prescriptions for recovering for modeling the distribution of satellite galaxies. It also incorporates galaxy assembly bias. So, and this model has been shown to be very good in reproducing the clustering, the multiples. Well, the predicted clustering, the multiples, and galaxy-galaxy lensing for stellar mass selected galaxies from the TNG simulation. So then we went to the same sample of color-selected galaxies, the post-TNG sample, and we fitted again what I was saying before, projected clustering and the monopole and quadrupole and galaxy-galaxy lensing. And what we found, the red line, is that we can reproduce all these different observables within error bars. So there is no longer a lensing slope problem when we use a more sophisticated model like SAME. Another important point is that when you don't consider galaxy-galaxy lensing, you find that there is a huge discrepancy on this observable even though you are fitting the other. Why is that? Because the galaxy-halo connection for this model is very flexible. And if you don't increase the constraining power by including extra observables, the predictions are, the centrality of the prediction are very large. If we were to put error bars here, this blue line will be still compatible with the dots, but you can see the best fitting value will be for this other observable will be a bit far. So now that we were sure that the model works in a controlled environment with when fitting the post-TNG sample, we went to observations and to fit the clustering and lensing, now both because of what I was saying before, of both galaxies by evaluating the model in two different simulations, in a simulation with a Planck cosmology and another one with a low sigma cosmology. And what we found is that for neither of these cosmologies, there is a lensing slope problem. So we can fit both projected clustering and galaxy-galaxy lensing within error bars in both cases. We found this for all the different samples of the post survey. You can see this here for all the different recipes. So, yeah, so what is happening here is that in reality, because there is much more flexibility, you can fit both observables. So what we need and what we are working now is that in modeling additional observables, so we can break this degeneracies in the cosmology that we find, because the prediction, for example, for galaxy-galaxy lensing under the Planck cosmology and the ΛCDM cosmology are different. But just to recap and to go to the important points, that what we found is that standard empirical models don't account for multiple galaxy formation effects that are predicted by our base models of galaxy formation, that are the dynamical simulation and the segmentation models. And these galaxy formation effects affect very strongly galaxy clustering and galaxy-galaxy lensing on small scales. Empirical models that don't account for this effect can still fit galaxy clustering without problems, but to accommodate for the impact of this effect on the galaxy-fellow connection, they overpredict galaxy-galaxy lensing, and this results in the lensing slope problem. Using a more sophisticated model like SAME, what we find is that there is no lensing slope problem, but this comes at the cost of losing some constraining power, because we need this additional flexibility. But in the end, this is not a bad result. What it means is that in order to get unbiased constraints on galaxy formation cosmology, we need more sophisticated models, and because of that, we need additional data. And right now, we are modeling on improving the predictions of this model for additional observables and to fit cosmology using all of them at the same time. Thank you.